In steady state exercise, there will be a higher saturation of oxygen in the hemoglobin as there will be a higher demand compared to the no exercise. Aerobic system. The aerobic system involves the oxygen transportation system and the use of mitochondria in the working muscles for oxidation of glycogen and fatty acids. It is known as the aerobic energy system because of its reliance on oxygen. This system involves prolonged work at low intensity and increased importance in the longer of the sport duration. Lack of fuel, overheating, or dehydration will end the exercise. Fueling this system for combustion varies according to its duration and intensity. In prolonged aerobic exercise, the preferred fuel is fatty acids because the glycogen stores are limited compared to our plentiful fat stores. Unlike glycogen, fatty acids can be used in the aerobic system, whereas higher intensity exercises involving aerobic and anaerobic energy systems prefer glycogen as fuel. Muscle spindles. Muscle spindles are proprioceptors found in skeletal muscles. They detect muscle stretch and initiate a reflex that resists the stretch. When muscle is stretched, primary sensory sensors in the muscle spindle respond to the velocity and degree of stretch, then send the information to the spinal cord. Secondary sensory sensors detect and send information about the degree of the stretch to the central nervous system. This information is transmitted to a motor neuron, which activates the muscle to contract, thus reducing stretch. The Golgi tendon organ is a proprioceptive sensory receptor organ that senses changes in muscle tension. It lies at the origins and insertions of skeletal muscle fibers into the tendons of skeletal muscle. Cardiovascular system. During steady state exercise, we use several devices to measure the heart rate of the participant. We hypothesize that the heart rate will increase during the exercise and will do so in relation to the intensity. This means that there will be an initial increase in heart rate due to anticipatory rise. When exercise starts, the heart rate will carry on to increase until it reaches its steady state level, which will be 70 to 80% of the participant's maximum heart rate. This will be about 3 to 4 minutes in. The heart rate will then plateau for the remainder of the exercise. It will then decrease when the exercise is finished, as there isn't a high need for oxygen to the muscles. For the first 10 minutes of the exercise, the participant was working too hard, and this was shown as the heart rate was at 187 beats per minute by the 10th minute. The BPM told us that the participant was working between 80 to 90% of his max heart rate. This was also shown by his RPE as it was quite high. He then lowered the intensity for the remainder of the exercise, where he was then working at 70 to 80%, also known as steady state exercise. Respiratory system. During steady state exercise, we counted the breaths per minute from the participant to see how many breaths they were taking per minute. We hypothesized that the breathing rate will increase during the exercise and will do so in relation to the heart rate. This means that there will be an increase in breathing rate when exercise begins. This will keep on increasing until it reaches its steady state level, which will be about 3 or 4 minutes into exercise. The breathing rate will then plateau for the remainder of the exercise. It will then decrease when the exercise is finished, as there is no longer a higher need for oxygen. For the first 10 minutes of exercise, the participant was working too hard. This was shown as his breathing rate was at 48 by the 10th minute. This was his highest breathing rate. He then lowered the intensity for the remainder of the exercise. When he did this, his breathing rate declined and started to become steady state. energy system. During steady state exercise, we used a lactate probe to measure lactate levels and an oximeter for O2 saturation. We hypothesized that the aerobic system would be the most significant system being used. By measuring the lactate, we can establish the use of an anaerobic glycolysis as a source of energy. Our hypothesis stated that there would be no lactate in the blood recordings. When we used the oximeter, there were results that can suggest if a low score of O2 is recorded, then not enough of O2 is being provided. Therefore, another energy system was being used. This would give us more evidence to support the hypothesis that aerobic glycolysis would be evident during steady state exercise. Hypothesis overview. For the cardiovascular system hypothesis, it did not match the raw data that we collected when conducting the test. It only did this towards the end when the subject lowered the intensity that they were working at, but by this stage it was too late. To be able to get good results, we would have to redo the test so that it would match our hypothesis. For the respiratory system hypothesis, some of the raw data matched it, whereas some didn't. It did this at the beginning of the test where there was an increase in breathing rate. However, there was no plateau for most of the exercise. But at the end, the breathing rate did decrease like we hypothesized, as there was no longer a higher demand for oxygen. To be able to get better results, we would have to redo the test so that the data would match our hypothesis completely. For the energy system hypothesis, it did not match any of the raw data that we collected from the test. We were meant to see hardly any lactate from the subject. However, there was at most 17, which is quite a lot for an aerobic exercise. This told us that the subject was working too hard, so that during the exercise they were using a different energy system. To be able to get correct results, we would have to repeat the test again.